Hi guys, in this video we are going to talk of bit manipulation. So firstly we'll be talking of the operation, that is the XOR and or not and the shift operations. In shift we further have the left and the right shifts. Then we'll talk of tricks that we can use in bit manipulations, and then we'll be talking of the use cases of bit manipulations. So with that, let's get started. So firstly, if you are already familiar with the binary representation and the decimal representation, you might want to skip the first 5 or 6 minutes of this video, because I'll be talking in a very new perspective. So even if someone has no idea of what a representation basically means, or what's a binary or a decimal representation, even he's able to understand all the concepts. So if you want to skip that, you can skip the first maybe 5-6 minutes. So let's talk about number representation, right? So on daily basis we see a lot of numbers, and the numbers we see on daily basis are actually represented in a decimal format. So what a decimal format means? So decimal format means is that we are going to represent any number in a decimal format. Yeah, I know that sounds stupid, but let's see what it means. So I have digits 0 to 9. So I have 0, then I have 1, I have 2, so on to 9, right? From this set of digits, I want to represent a number. So am I able to represent every number from these digits? Definitely yes. So let's say I choose a random number. Let's say 1, 2, 6, 8, 7, 9. This is just a random number. Now all of the digits in this particular number belong to this set only, right? So cool. So in the same way, all the numbers we are seeing on daily basis actually have digits only from this particular set, and hence they are called decimal numbers. So now we know what decimal representation is. Also over here, if you note, so what happens is that the index at, or the number at the 0th index, right, has a power of 10 to the power 0, right, or the a magnitude or a value, you can say, of 10 to power 0. A number at this first location has a magnitude of 10 to power 1. The number at second location has a magnitude of 10 to power 2, so on. Or in other words, let's say I have a smaller number, let's say 143. This is a smaller number, so I can write it as 3 into 10 to power 0, then 4 into 10 to power 1, then 1 into 10 to power 2, and then I can add them up. So let's add them up. I'll get 100 plus 4 into 10 is 440 plus 3. When I'll add them up, I'll get 143. So now I think you understand how we represent numbers, right? Now what if I tell you that we don't have 10 digits in total, but we just have let's say 2 digits or 3 digits. So let's talk of 2 digits. So we have only 2 digits. Let's call them 0 and 1. So using only 0 and 1, we want to represent all the numbers. Now is it possible? Yeah, it's definitely possible. What we can do is, like over here we had 10 numbers in total. So what we were doing is that for the number at the 0th index, we were multiplying the number by 10 to the power of I. So you can like generalize this particular thing, the thing we just wrote over here. So you can generalize this as summation of I is equal to 0 to n. Then you have a bi. So bi is basically the number or the coefficient. Like bi is b0 is 3, b1 is 4, and b2 is 1, right? So then you can say bi into 10 to the power I. I hope that's making sense. Now when we sum up all these values, we'll get the actual number. Can we apply the same thing over here? Yes, we can. So we can say that the number would be from I is equal to 0 to n, that would remain same. I'll also have a coefficient. Now the coefficient would range from 0 to 1 over here. The coefficient over here for this decimal representation was ranging from 0 to 9. Cool. And then when I'll multiply, so I'll not multiply it by 10 to the power 1. I'll simply multiply it by 2 to the power I, right? So let's see what I mean by this. So let's talk of a smaller number. Let's say I'm talking 12, right? So 12 is simply written like this in decimal format. But can I write it in binary format? By binary format, I mean that I only have 2 digits to represent the entire number, that is 0 and 1. So can I represent it in a binary format? Yes, I can do that. Now how I'll be doing that is, I'll say okay, so the first power or the number at the 0th location would be multiplied by a power of 2 to the power 0, that is actually 1. So let's say it's 0 over here, right? Then again a 0, so this number is multiplied by a 2 to the power 1. Then I'll have a 1 over here. This number is multiplied by 2 to the power 2, and then I have a 1 over here. So this number is multiplied by 2 to the power 3. Now let's see what this value comes out to be. So this would be 1 into 2 to the power 3 plus 1 into 2 to the power 2 plus 0 into 2 to the power 1 plus 0 into 2 to the power 0. So that becomes 1 into 8 plus 1 into 4 plus 0 into 2 plus 0 into 1. Now these are zeros. This is 4, this is 8. Now 8 plus 4 is equal to 12. So yeah, we can say that we are able to represent a number in the binary format. Now there's a proof to it. You can like Google it up if you want to, but the thing is that all the numbers can be represented in any format. So I can represent 12 like this. I can represent any number in the binary format. I can also represent any number in the ternary format, or whatever you may call it. So basically, if I'm only having 3 digits, I can represent any number in that also. If I'm having 4 digits, all the numbers can be represented in that also. So for any number of digits I have, it would be possible for me to represent all the numbers in that format. Cool with that. But how do we do it? Like over here, I told you how to represent 12, but is there a defined algorithm for it? Yes, there is. But to simplify, if we want to convert any decimal number into a binary number, what we can say is that we'll keep dividing the number by 2, right? So we'll keep dividing the number by 2, and if the number that we currently get is odd, then we'll append a 1. Now I think it might have made sense, it might not have made sense. Let me clarify this further. So over here I was having a number 12, right? I'll firstly check that if the number is odd. If the number is odd, then I add a 1. If the number is even, then I add a 0. Cool. Is the number odd? No, it's not a odd. So add a 0. Now divided by 2, I'll get a 6. Now is the number odd? No, it's still not odd. Okay, get me a 0. Now I'll again divide it by 2, I'll get a 3. Now is the number odd? Yes, the number is odd. So give me a 1, right? For 3 divided by 2. But now when I'll divide it by 2, I'm taking a ceil operation, or you can say a integer division. So 3 divided by 2 is basically 1.5, but I'll not be considering this, right? So 0.5 is not being considered. So I'll be getting a 1. Now is 1 odd? Yes, it's odd. So give me a 1. Now 1 divided by 2 would be 0.5, but we'll since we are truncating anything after the decimal point, we'll be saying it's a 0. So our check ends over here, and this is the number we have received. So yeah, we have already calculated that the binary representation of 12 is actually this only. So yeah, this makes sense, and this is the defined algorithm for us. So basically what the algorithm is, while the number is greater than 0, what you need to do is, if the number is odd, then add 1. If even, then add 0. And in each iteration, what you have to do is that number is number divided by 2 itself. Cool. With that, I guess the logic or the fundamental behind binary representation is somewhat clear. So now we can move ahead. So with that, what we know is that every number can be represented in binary format. So 12 was actually 1100. Now 13 would be 1101, right? What would be 20? So 20 can be represented as 16 plus 4, right? So I'll write 16, and there's a 8, then a 4, then a 2, 1, right? So this basically means 20. Don't worry, as you practice, you will be able to like see the number and tell its binary representation. It's not something that you always need to remember by heart, but it's always like as you solve more questions, you do more problems, you'll definitely start remembering some such sort of things. Cool. With that, let's talk about the binary operations. So what are binary operations? Like we have addition, multiplication, division. When we are talking of decimal representation of numbers, we have something called binary operations or bitwise operations. Now why bitwise operations, right? Why are we calling it bitwise operations? And one more important thing is that why do we even need bitwise operation, and why are these important? So as you know that a computer can only understand zeros and ones, right? So we can only feed a computer with values zeros and ones. So whatever we are writing in the computer is actually getting stored in zeros and one format. Also, if we are storing any number in the computer, it gets stored in a 0 1 format, right? So it's getting stored in this particular format, that is a combination of zeros and ones. Now, since every number is being stored in 0 and 1 format, if we are able to perform bitwise operations on that, and by bitwise operation I mean if we are directly able to manipulate the bits in that number, so we can do a lot of interesting things with that. Cool. So that's why bitwise operation in particular is a very interesting topic, or a very useful topic for all the computer science engineers out there. So cool, let's talk about the first operation we can perform on bit, that is the AND operation. So what is the AND operation? So firstly, let's talk of two numbers. Let's say I'll take 12. I don't know why I'm writing 12 again and again, but cool, no worries. And I'll take, let's say, 14. So the representation of 14 is 1110, right? Now I say AND it up, AND these two numbers up. So what ANDing does is that, so when we perform any bitwise operation, we perform the bitwise operation on the bits at the same index. So this is the index 0, this is the index 1, index 2, index 3, right? Cool. So when I'll be performing the bitwise operation, so for 0th index, I'll be checking the bits of these two numbers. For the first index, I'll be checking these bits, right? And I'll be performing the operations on these two numbers, then these two numbers, then these two numbers. So what is the AND operation? In AND operation, if both the set bits are set to 1, so if I'm having a 1 and a 1, only then my output would be a 1. If I'm having a 1 and a 0, then my output would be 0. 0 1 would also give me output 0, and a 0 0 would also give me output 0. So the only case where I'll be having a 1 is actually 1 1 itself. So let's do it for this. So over here, let me change the color. Cool. So over here I'm having a 0 and a 0, so the answer also would be 0. I'm having a 0 and a 1, so my answer would be 0. I'm having a 1 and a 1, so my answer would be 1. I'm having a 1 and a 1, so my answer would be 1 over here as well. So what's the answer I got? It's 12. Now just to practice, we can say that if you had another number, let's say 5, and the other number was let's say 3, so this is 5. Okay, messed it up. Cool. This is 5, this is 3, right? So for first bit, it would be a 1 and a 1, that would be a 1, then 0 and 0. So their AND operation would give me a value of 1. I hope that's clear. So that was the first operation we learned, that is the AND operation. Do we have other operations? Yes, let's talk about the OR operation now. So what's the OR operation? In case of a OR operation, if you are having, like we gave this table for the AND operation, we can also set a table for the OR operation. So if we are having a 0 and a 0, we'll be getting a 0. But if we have a 0 and a 1, we'll get a 1. 1 0 would also give us a 1, and 1 1 would definitely give us a 1. This is about the OR operations. Now I'll ask you or urge you guys to actually try doing some OR operations on your own and try to make sense of it. In the interest of time, I won't be solving problems over here, or all the problems, or all the solving for all the operations. So let's go for other operation, that is called the NOT operation. So what is the NOT operation? In NOT operation, we simply invert the bit, right? So let's say I say NOT of, or I want to invert the bits in a certain number. So let's say I have a number 12. Let's write it in binary format. Let me give another number. I've written 12 a lot of times. Let's say it's 6. So 6 basically is this, right? Okay, so it's 110. Yeah. So I say I want to invert it. So what I can do is I'll toggle all the bits. So it would become 0 0 1, right? What if I have 1? So 1 would become 0. What if I have 0? So 0 would become a 1, right? So that's about the NOT operation. Now there's another interesting operation that's used a lot of time, that's called the XOR operation. So what a XOR operation does is that if both the bits are set to the same value, then the final output is 0. If both the bits have a different value, then the final output is 1. Or more formally, I can say if I'm having a 0 0, then my answer would be a 0. If I'm having a 1 0, then my answer would be a 1. If I'm having a 0 1, my answer would be a 1. However, if I have a 1 1, now even in this case both the bits have the same value, then also my answer would be 0. So this is called the XOR operation. We used it a lot of times while solving problems for like general problem solving things in DSA or even in competitive programming. Cool, I think that completes the operation we wanted to do. Now let's talk about the shift operations. So what are shift operations? So let's take another number for reference. So let's take 20. So 20 basically is 16, then 4, 0, 0. This is basically 20, right? So if I say that right shift this number by 2 units. So what you will do is you will shift this number. So all of the values would get shifted by 2 units. So let's say this was the representation 1 0 1 0 0. Now I'll say shift all the bits by 2 units to its right. Cool. So what would they become? So they would become over here new numbers would come. So let's say all the numbers that would come over here are actually zeros. So this would be 0. This also would be 0. Now this, okay, let me change the pencil. Cool. Now this particular number would come exactly over here. So this would be a 0 0. This one would come exactly over here. This one would come exactly over here. Right. Now what about this one? This one would come somewhat over here, but my answer is actually complete till this particular point itself. Right. So what about these two numbers? We are going to discard them irrespective of whatever their value was, since we shifted them like 2 places to the right. So the last 2 digits would be discarded. If we had shifted them by 3 places, then the last 3 digits would have been discarded. So this is the shift shift operations or shift right operation. Now what's the significance for this? So let's try to understand the significance. The value of this is basically 5, right? What was this value? This was actually 20. So our 20 became 5 when we shifted it by, when we right shifted it by 2, right? Also, if you notice that 20 divided by 2 to power 2 is actually equal to 5. So that's making some sense, right? Now what if I had shifted it by single number? So this is my 20, right? So had we shifted it by single number, so this would have given us 0 1 0 1 0. Now what's the value for this? So this value is actually 0 plus 2 plus 8, right? So its value is 10, which is basically 20 divided by 2 to power 1 or 20 divided by 2. So in other terms, I can say that if I right shift a number by I units, right? So if I right shift a number by I units, then it's equivalent to dividing that number or that number x by 2 to power I. I hope that's making sense. Similarly, when we are talking of left shifts, then what I do is that, let's say if my number was 1 0 1 0, this was actually we took example of 20, so let's carry on with 20 itself. So if I right shift 20 by, let's say, 1 unit, so my answer would be 1 0 1 0 0 0. I'll be shifting them 1 places to the right, and then to fill this gap I'll be appending a 0 over here. So 0 is appended, then this 0 comes over here, this comes over here, 1 0 1. So this is the number I get, right? So what's the value of this number? So this is 0 1 2, okay, sorry, 1 2 4 8 16 32. So 32 plus 8 is actually 40. So this is actually 32, this is actually 8. So 32 plus 8 is actually 40. Now also we can say that 40 is equal to 20 into 2 to the power 1. Cool. So you can actually check for 80, then for 160 as well. I'm not going to do it over here. So this basically means if we left shift, then it's equivalent to making the number x would become x into 2 to power I. I hope that made sense. So this is for the left shift, and for right shift we were basically dividing the number by 2 to power I. Cool. So enough of theory. Now let's see some code, some actual code that would maybe give you some perspective. So this is a standard boilerplate code, I'll say, but over here I've just defined a method. So you need not worry about the implementation. The only thing it's doing is it will be giving you the binary representation of that particular number, that the number we will be talking about. So let's say I give it a number, let's get rid of 12, let's talk about 20. So yeah, let me give it a number 20. Let's see what the binary representation is. Okay, so over here you can see the binary representation. The number of zeros are too much because I have selected it to give the number in a 32-bit format. Let's reduce the number to 5, or let's say 6 units or bits. Okay, so the binary representation is 1 0 1 0 0. That is something we already said, right? Now let's try to right shift it. Now how do I like left shift or right shift a number in my code? So in C++ you can write something like this. So it's a double less than sign. So what it does, it left shifts your number. So the way to remember is that since a left shift, since this particular expression has a arrow that is pointing to the left itself, so it will left shift your number, not shit your number. Cool. So then what would this do? This kind of a expression would actually right shift your number. Let's see this in practice. So let's say I say that I want another number. Let's call it A, and the value of it should be number, and the number should be right shifted by, let's say, 1 unit. Cool. And then I want to see the value of A as well, so I'll write print binary for A also. Cool. Let's see this, if this works. Cool. So you can see that the number 10100 was actually right shifted by 1 unit. Let's also try to print the values of the number so we can validate our claim. So this was num and this is A. Wait, let's try it out. Cool. So over here you can see that this was the binary representation of 12, and then we got this number by right shifting it by 1, and this number actually corresponds to 10. Now let's try to left shift it. We'll left shift it by, let's say, 2 units. I'll have to increase the size of the bits. Okay, let's try it out. Cool. Now since we shifted it by 2 units, we should have got the answer 20 into 2 to the power 2, that is 20 into 4, that would have been 80. So over here we are getting answer 80. So our concept of at least right shift and left shift is clear. Cool. Now let's talk about the simpler things, that is the AND and the OR operation. So the AND operation in CPP is actually represented by AND. So we have this is the AND operation. Let me make some comments over here. Cool. So operations. So the AND operation is represented by AND. The OR operation is represented by this vertical line, you can say, or whatever you want to call it. What about a NOT operation? So NOT is simply represented by the exclamation mark. Is there anything else? We talked of shifts, right? So shifts are actually represented by either less than signs or greater than signs. So 2 consecutive less than or 2 consecutive greater than for left shift and right shift respectively. Is there anything else? Not really. I can like perform everything using this. Let's try to take an example. Let's try to use the AND operation on 2 numbers. So let me have a number A. I already have a number A. Let's try to delete it first. Let's try to delete everything maybe. Cool. So let's say I have a number A whose value is 12. Cool. And then I have a number B whose value is 6. Cool. So then I'll try to print the AND of A and B. Let's see what it gives us. Okay, it gives us an error. Okay, I'll just use the parenthesis over here. Cool, we get a value 4, but why is that the case? So in order to understand it, let's try to print the binary representations as well. Print binary for A, then we can say print binary for B, and then we can also print the binary for A and B. Cool, let's try them out. Okay, so the binary representation for A or 12 was 1100. The binary representation for B, that is 6, was 110. And when we ANDed them, so over here you can see that the bit or the index at which the bit was set for both the numbers were actually this particular index, or the index 0 1 2. So at the index 2 the answers bit was also set, and for all the other indices it was unset. By set I mean it was set to 1, by unset I mean it was set to 0. So at the end my answer was 4, because 100 in decimal format is actually 4. So now let's try to perform some more operations. So what I can say is that, let's say I have to check whether element is odd or even. So for an odd element, the digit at the last location would be 1. So what I mean by that is that the digit at the 0th location would be 1. So over here all these numbers were actually even, because the number at the last location was actually 0 in them. Now let's talk of odd numbers. So odd numbers are actually 1, 3, we have 5, we have 7, right? Now 1 is represented as simply 1, 3 is represented as 1 1, 5 is represented as 101. What about 7? So 7 is represented as 111. So over here you can see that the digit at the last location is actually 1. Now why is this the case? This is because when you are representing the number in the binary format, so the numbers are technically written in the powers of 2. So it's 2 to the power 0, then we have 2 to the power 1, then 2 to the power 2, so on. So if you have 2 to the power of any positive number, then it always would be divisible by 2, or in other words it would always be an even number. However, over here which is 2 to the power 0, it comes out to be 1. So now if we add 1 to any even number, it becomes odd. And that is the reason that if the but if the starting or the element at the 0th position is actually set to 1, that simply means that we were adding 1 to the number, and thereby the number is even, right? Or the number is odd, sorry. So let's try it for a few numbers. I'll check if my a mod 2. So why a mod 2? Or I can actually say a and 1. So a and 1 would basically mean that I have a. So a in binary representation, and then I'll also be having 1 in binary representation, right? In binary representation. So a would be something like, let's say if I'm saying a is equal to 12, so it would be written as 1100. What about 1 in binary representation? It would be written as 1, but since we want the same number of bits, so we'll append zeros before it. Cool. So this is basically my 1. Now what would happen is when I'll AND it up, so if you remember, when we AND two numbers up, then the bit that is set in both the numbers is only present in the final answer. So over here, since 1 is in the second number, that is 1, only a single bit is present. So now the final answer would be non-zero, or would be 1, only if the same bit is also made 1 in a number, right? I hope that was making sense. So now I can check if the first bit is set in a, then I can say it's a even, right? Otherwise, okay, so I can say it's odd. Really sorry for that. Otherwise I can say it's a even. Let's try that out. Cool. It's saying it's a even. I can change the number to 11. Let's say it will say it's odd. Let's try a bigger number. So maybe this. Yeah, it's an even number. Let's change it to something odd. It's saying it's an odd number. So cool. With that, we learned one more concept, and how we are using bitwise manipulations over there. Now let's say what I want you to do is that you are given with a number and its binary representation is something of this sorts. Let's say this is the binary representation of that number. Now I ask you to make a certain element or a certain bit as 1. So I ask you make this particular bit as 1. So how you would be able to do that? Let's see it in practice. So let me write a very random number. Let's say this is the number I wrote, and firstly let's check its binary representation. So its binary representation would be given by this. Let's check for the binary representation of this number. Cool. So this is the binary representation of this number. That is 0 1 1 0 1 0 1 1, or maybe it could be something different, but I've kept it to 32. That's why. Let me run it again. Let's see. Yeah, it was actually different. So this is the binary representation of the number. Let me copy this, let me paste it over here. Yeah, okay, so this is the binary representation of this number. So now what I want you to do is that take this particular 0, this one, and make it a 1. So how would you be able to do that? So a tricky way of doing it, or an easier way I'll say of doing it, would be that think of another number. So since we wanted this particular thing to be set to 1, what I'll do is I'll take all zeros, right? So this is my number A, let's say. This is my number B. This is a new number I've taken. I'll take all zeros and I'll only make this particular bit as 1, right? And now I'll OR them up. So in OR, if you remember, in the final value, a bit is set to 1. If either of the values would have a 1 bit set, right, it would be set to 0 if both the values have zeros, or if both the numbers have zeros as the bit at that particular index. So now the answer would become 1 1 0 1 1 1 0 1 1 1 1 1 0 1 0 1 1, right? So we got the final answer. So basically I want to have a single bit set that would be the bit at the required location, and then I'm gonna OR that particular element. But how do I get this particular number? So now ORing it is easy. For OR I can simply use this, as we know, right? So this is the OR operation, or the OR operand, so we can use that. But how do we get this number? So let's call this number A. So A we already have. We want to make a number B. How can we get B? For B, what I can say is that initially my B is set to 0. So 0 is, all the bits are set to zeros. And then I'll say that let's OR it with, or I can actually take my B to be 1 shifted this many number of times at whatever location I wanted. So I want this particular bit at location 0, 1, 2, 3, 4, 5, 6 and 7. So I can say that shift my 1 7 to this 7th location, right? Or shift the 1 by 7 units to the left. So so initially it would be 1, after the first shift it would become 1 0, then 1 0 0. Finally after the 7th shift it would become 1 followed by 7 zeros, right? So let's try it out. So what I'm saying is my B basically is 1 shifted by 7 zeros, right? And then I'm going to, okay, so let's store the value of the OR in another variable so that you know exactly what's happening. I'll simply OR these two values up. Now let's see the value of C as well. Let's rather see the value of A, B and C, so as to get more clarity. So this is my B, this is my C. Let's check it. Cool enough. So this is the value we finally got. This is the value of B. So let's see if the value of B is exactly what we wanted. So I'm just gonna copy paste this. So let's see if it's exactly the same. Yeah, you can see that this value was the exact value that we wanted. And now let's check for C. So in C you can see that this is the final answer we got. So this answer is exactly similar to this. The only difference is that the bit at this particular location is actually set to 1, and that's what we wanted. So yeah, cool, we can do it in this fashion. So this way we can actually unset it, right? Or we can actually set the bit at the ith location. So setting the bit at ith location is now known, right? What if we want to unset this bit? How would we how can we do that? So for that, what I can say is, so there are multiple ways of doing it, to be honest, but a very intuitive way for me is that firstly I'll check if the bit is set in A or not. If it's not, then I'll set it, right, or I'll unset it. But other way of doing it, I can actually toggle it. If I already know that the bit is set to 0, let's say, then if I toggle it, it would become 1. If it's already set to 1, then it will become 0. So these are the way. Is there any other way of doing it? Yes, there is. So I can have my B now to be all ones, right, followed by a 0 at the location I want to unset it, followed by all ones, and then I can say that my B would now, okay, then I can say that I'll AND my A and B, right? And when I'll AND them up, so now in case of an AND operation, 1 persists only when both the bits are set to 1s, right? So the answer of A and B would become 1, So let me erase this so as to get more clarity. Yep. So my answer would become 1, since I'm having 1 at both locations, then 1, then 0, then 1, 1, 1, then a 0, then a 1, 1, then a 0, then a 1, 1, then also 0, right, then a 1, then a 0, then a 1 and a 1. Yeah, so this is definitely something I can do. Let's try it out with the same example. So over here, this is the number we are having. Let me try to unset a bit. So let's say, let's unset this particular bit, that is the bit at the 0, first, second or third location, right? So I want a number that would be similar to this but would have a bit over here to be 0, right? And then it can have all the values as ones. So how can I get this number? I can use the same logic. So initially I can say that my b is this, over here it would be 3 because I want third index value set to be 1, and then I can invert the bits. I can make all the zeros values as 1 and all the ones values as 0. So for that I can simply say b is equal to naught of b, right? And then my answer would be a and b. Now let's try it. Okay, so yeah, I wanted this particular like value to be 0, and then I wanted to AND them up. So you can see as soon as I ANDed them up, so the bit at this particular index, that is the index 3, is now set to 0. All the rest bits are unchanged. So that is exactly what I wanted, because I simply wanted to unset this bit. Now what if I wanted you to, or I wanted me to toggle this bit? So by toggling, what I mean is, if it's set to 1, then I wanted to make it 0. If it's set to 0, then I want to make it 1, right? How can I do that? So if I want to do that, then I'll follow this particular logic itself, right? And then over here, instead of ANDing or ORing, I'll simply do a XOR operation. So why is this the case? Because in the number b, I'm only having one bit set, that is the bit corresponding to the index that I want to toggle. And as soon as I XOR the number by b, so what would happen is, for the rest of the bits, b would be having a value of 0. So they would remain untoggled, because you know that when we toggle, so if both the values are same, right, in that case the value is 0. So for example, if both the values were 0 and a 0, it would still remain a 0. If it was a 1 and a 0, it would be a 1. That is something we wanted. If it's a 0 and a 1, it would be a 1. If it's a 1 and a 1, it would be 0, right? So you can say that if my value in b was a 1, then it's actually toggling it. So if it was a 1, then it actually toggles it, because the 0 becomes a 1 and a 1 becomes a 0. In other cases, if it's set to 0, then it's not toggled. If its a value is 0, then a 0 and 0 would give me 0. If it's a 0, then a 1 or 0 is gonna give me 1. So these cases are not toggled, or we can say same, and these cases are toggled. Cool enough. So with that, let's try to do the same over here. Let's try to run it. Let's see what happens. Okay, so over here you can see that this was my b, and I just wanted to toggle this particular value. So as soon as I XORed it with it, so this value was set to 1, so it got toggled to 0. So now this value is 0 over here. The entire rest of the entire answer remains the same. Cool. With that, we are done about toggling, setting the bit, unsetting the bit. And frankly enough, this thing was good to know, because you can actually use this particular logic at a lot of locations and at a lot of places as well. Now let's talk more about bits itself. So let's say I wanted to maybe have a number, and the number should have ones from 0 to L location, right? From 0 to L, it should be all ones. How can I do that? So for that, I can use a simple logic. So I know that if I'm having a number, let's say 101 followed by any number, all zeros, and if I subtract a 1 from it, so let's say if I subtract 1 from it, so what would happen is, over here there would be a carry. So at the first location also I'll be having a 1, right? I'll be having a 1. Okay, so it's a bit tough to explain this way, but anyway, cool, let me try. Okay, so over here I'll be having a carry. I'll be having a 1. This carry would get, like received from here, so it would also become a 1. I'll be having a 1 over here at itself, then a 1, then a 1, then a 1. I think you understood what I'm trying to say. So I'll be having all 1s, right, followed by a 0. So this is understandable, right? It's similar to saying that if you subtract, let's say this is a number in decimal format. So in a decimal format, let me write 1000. What if you subtract a 1 from it, right? So you subtracted this from this. So what happens is that initially for the 0th index you get a carry and you received a 9, right? Then you receive another 9, another 9, another 9, another 9, so on, right? Yep. So this is the answer you're gonna get. The same thing is gonna happen over here. The carry logic actually remains same irrespective of the representation or the base of the representation. So that logic would still be applicable. So this is one of the observation I have. So if I want to make all of these values to be 1s, right, or if I want to set all values of a number from 0 to minus 1 bit to 1s, then what I can do? So I can firstly say that I want to set the lth bit to be 1. So I want something like 1 all and followed by l minus 1 zeros or l zeros, and then I can subtract 1 from it. So as soon as I'll subtract 1 from this, all of these would become 1 and this would become 0. Let's see this in practice now. So let's say my a is 1, right shifted by maybe 10 units, and my b is okay. So my b is a minus 1, right? Let's try to see what are a and b's. Okay, it gave an error. Yep. Okay, over here you can see that the a was 1 followed by 10 zeros, right? And my b is exactly 9 ones. So I hope that made sense. So with this we learn how to set all the bits from the 0th, so this is the 0th index, to the l minus 1 index to 1s. So is there more to learn? Yes, there are a lot of things, but to keep the video short, I'll be closing the video soon. So let's learn one more thing. How to check if a number is divisible by 2. Not divisible, but let's say how if a number is a power of 2. So the power of 2's are 2 to the power 0 is 1, then 2, then 4, then 8, then 16, then 32, then 64, then 128, 256, so on and so forth, right? So the interesting thing about the powers is because whenever we are representing a number in the binary format, we are actually talking about the powers of 2. So if you remember, we are actually adding up the powers of 2's. So what we can say is that if a single bit is actually set in the number or in the binary representation, only in that case my number is a power of 2, else it won't be. Now how do we check the number of bits? You can actually perform a mathematical way. You can keep checking all the bits that are present, or there is a built-in functionality that is called built-in pop count. So let me show you that even. So let's say my number was 16, and then I use a built-in functionality called built-in pop count. So built-in pop count. Make sure that the underscores you are using are perfectly fine. It shouldn't be like 3 underscores followed by a single underscore. It has to be 2 underscore followed by built-in followed by underscore, then pop count, right? So pop count a. Let's see what it gives me. So I'll try to print my count. Also I'll try to print the binary representation of a. Cool. Over here this is the binary representation of a, and this is the pop count. So I can say if count is equal to 1, then it's a power of 2. See out power of 2, else it's not a power of 2. Not of 2 factorial, but 2, yeah. Okay. Anything else I can do over here? Let me take another example, because 16 we already know is power of 2. Let me take a bigger number like this, something of this sorts. Let's try it up. Yeah, so over here this is a big number, and the binary representation actually contains 16 ones in it. So you can calculate the number of ones. I won't be doing that, it's just a waste of time. So this functionality is known, and it's not a bug that it will give you a wrong answer. So it's returning me the number of ones in it. If the number of ones are more than 1 itself, then I can simply print it's not a power of 2. Now let me talk of a power of 2. Let's talk 2048. So 2048, if you don't know, is actually 2 to the power 11. 2 to the power 11. Now let's check this. Cool. So it checked for 2048. It checked that it has single 1, and then it printed it's a power of 2. Cool. With that, we also finished this, how to check if a number is power of 2. There are more concepts that I can cover, but this video is actually getting too long. So I really hope you learned these things that I wanted to explain. So I'll be covering the last thing, that is use cases, right? So let me discuss just one use case. So where all can you use it? So it is extensively used in DP. So what could happen is that the number of elements you are having is, let's say, less than 32, right? So in that case, what you can do is, instead of maintaining a boolean DP, or when you want to check if a particular number has been processed or not, instead of checking it that way, what you can say is that each of the bits of my number, so I'll take a num, let's say int mask, so we generally call it mask, and I'll set it to 0. Now the value at each index would denote whether that particular number has been processed or not. So let's say if I processed a number that was at index j, so if I processed element at index j, then what I'll do is I'll simply make that bit at the index j equal to 1. So the way to do it would be easy. I'll just OR mask with the 1 shifted j times, right? So by doing this, then whenever I'm checking, whenever I wanted to check that if that particular index or the element at the index j has been processed or not, I can say if mask and the element at j, if these both have like if the mask has the bit j set, then I'll say that it was processed, cout processed. If that's not the case, I'll print not processed. Yeah, so that's it. This is how we generally use bit masks for DP. Now what's the benefit? So the benefit per se is that over here we just need one number for the entire logic, right? So we are just using an order of one space. But in case it had been if we would have used a boolean vector or something, it would have technically been order of n space, although n over here would have been limited to 32, but still it's a variable, so we would have called it order of n. So that is one of the benefits. The other benefit is it's faster. So doing a bitwise manipulation is always faster. So I can say that even if you are calculating a odd or even value, you can calculate it in two ways. So you can say if n modulus 2 is 1, then it's an odd number, or you can say if n and 1 is something or is 1, then it's an odd number. But this way is technically slower and this way is technically faster. So whenever you will be performing bitwise operations, your computations would be faster than going via standard route. So that's why this is beneficial, and there are many more use cases that you'll learn as you'll progress in CP. But this video was all about teaching you the concepts that are actually required. So I hope this video cleared a lot of concepts. If you still want me to cover more concepts, I'll be more than happy to do that. So let me know in the comment section below. Other than that, thanks a lot for watching this video.